So good afternoon, everybody. Thank you to the organisers for inviting me to speak, and also for putting together just a really great group of us to talk about earthquakes and faulting from really different aspects, but actually all kind of trying to get at the same question. So yeah, really thank you to the organisers for putting together such a great talk. So we're going to be sticking with where Duna talked about in the last talk, and sticking with Italy. But I'm going to be talking a little bit more about the central Apennines of Italy rather than the southern half. So in my talk, I'm going to talk about earthquake clustering, interaction of normal faults, and ultimately, what does this mean for seismic hazard? And this is a photograph from the 2016 earthquakes that happened in central Italy around the town of Amatrice that some of you may be familiar with or may have heard about. And as always, you know, this kind of work is never done by myself. I work with a big group of collaborators both across the UK and also in Italy and other places. So a lot of this work is also builds on a lot of what they have done in the past. So when I'm giving talks, I always like to start off with kind of my key questions and give the answers, I think, to what are the key questions that I'm going to try and answer, so you can see where the talk is going. So I'm going to start off by talking about what actually drives the normal faulting in the Italian Apennines. And what we believe is that the Italian Apennines is a zone of extension, and that extension is accommodated by normal faults and underlying shear zones. Now, these normal faults, how variable actually are their slip rates? And we can use data to show that there is a millennial timescale variability in terms of faults moving fast or slow, and we call this clustering and anti-clustering. What drives this variability, though, on the slip rate on these faults? Why aren't the faults just slipping at the same rate all the time? And we suggest that this is due to differential stress changes on underlying shear zones affecting the strain rate. And finally, why is this actually important to understand earthquake clustering, particularly from a seismic hazard point of view? And this is due to the difficulty currently in incorporating this into seismic hazard. And because the physical mechanism behind why do earthquakes cluster together in time is still debated. And what I will present today is a new idea we've had about why we get clusters of earthquakes. So why the Italian Apennines? So Duna gave a nice little introduction to the southern part of Italy. Relatively similar in the central Apennines. So it's a broad zone of active extension of about 3 millimeters per year of extension in a northeast to southwest direction. And this extension is taken up on a series of normal faults, which are orientated approximately northwest, southeast, and the majority of them dip towards the southwest. So this map over here on the right is a map of our active faults of the Apennines, and the red lines are the active faults, and the blue and the purple dots are points where we have data on the structural geology of the faults. Now, what we think is driving this extension is that there is a slab window underneath the Apennines. It's a remnant of subduction down the coastline, and because through this window there's what we think is that there's buoyant hot asthenosphere rising, and that's causing overall uplift over the region, and that's what's driving both the long wavelength topography, high kind of over the Apennines, and also the normal faulting. It's a great place to go and study and work, and there are the normal faults are really well exposed at the surface. So these are predominantly limestone bedrock fault plains, and this is what they look like. So they record motion over the last 15,000 years, so basically since the end of the last glacial maximum. That's due to a change in the erosion rate at the last glacial maximum. And as I said, as I opened, what we believe is that these normal faults at the surface are underlain by localized shear zones that extend between about 15 and about 24 kilometers depth. And this, to get an idea of what the shear zones are like in terms of their sort of geometry, what this study by Patience Cowie did in Nature in 2013 was they looked at quartz flow laws, experimental laws that we get from the labs, looking at tiny samples. And they related the strain rate with the stress in the Apennines from looking at the long wavelength topography and the strain rates across the faults. And they realized that the strain rate was proportional to the imposed stress to the power law of about 3. And this is important because what this implies is that we have discrete shear zones and localized shear zones within the brittle viscous brittle, lower crust. So when most people think about central Italy or certainly Geologists, the most recent earthquake that happened in this area was back in 2016. And this is a really weird sequence of earthquakes. So there were 3 earthquakes that happened from August to October 2016, where the largest magnitudes were 6, 5.9, and 6.5. And these all happened on this fault here. This is called the Monte Vetri fault, the one that's circled in orange. The first one also ruptured a little bit of this larger fault here. And this is really strange. This is a really strange sequence, partly because of the order in which it happened, but also the Monte Vetri fault had a very long elapsed time. So paleoseismology has been done on this fault, and that puts the age of the last earthquake at about 6,000 years before present, but also with fairly large errors on that, errors of several thousand years. So why did this fault have such a long elapsed time? Is that typical for this fault, or actually is this really unusual? And this is especially interesting to this sequence because actually prior to this sequence, within the database of seismogenic sources, this fault was down as a debated seismogenic source. You know, people weren't sure whether it was active or not. So it's really important to understand, why did this fault have such a long elapsed time, then all of a sudden kind of start up again in these earthquakes? So to look at this, we've used a technique called Chlorine 36 dating of fault scarps. And what this allows us to do is to look at the slip rates on faults over very long periods of time, and in this case, over 15,000 years, because that's how old the fault scarps preserved are. So this is a photograph of a fault called the Fiumicino fault. So the fault plane itself is, you can see, comes through this photograph, and it's very smooth limestone surface. So that's the fault up here. So what Chlorine 36 dating is based on is the fact that there are energetic particles, cosmic particles, that are being produced in supernova throughout the galaxies, throughout space. And these highly energetic particles are bombarding the Earth's surface. And when they hit the limestone, that causes the calcium atoms within the limestone to change to 36 chlorine. And we can measure the amount of 36 chlorine with a particle accelerator. And above the ground, the chlorine accumulates at a constant rate, but below the ground, what we see is that there is a tail off with depth. So this is the production rate of chlorine 36 as you go deeper under the soil. So what we can do is we can go and we can take samples using rock saw, which is pretty challenging work. I did a very small part of this, and just the one day I did was, or a couple of days I did, was really challenging. And what we can do then is we run this through the AMS, and we can plot the concentration of chlorine 36 against the height up the scarp. And what we would expect to see is that there should be more chlorine 36 up the scarp because it's being exposed for longer due to progressive slip from past earthquakes. So what we do is, once we've taken those measurements from the AMS, we then iterate for the slip history of this fault using a code published by Joachim Beck, which is a Bayesian Monte Carlo Markov chain code. And this code allows for variation in the timing of earthquakes, magnitude of earthquakes, and a number of other factors. So what does this data look like? So this is the slip history for the Monte Vetri fault. Note that this was taken prior to 2016, the samples were taken. And what we can see is that so the blue line is like our best fit, the least squared solution, and the colors kind of indicate the density of other models available. And what we see is that there's a change in the slip rate. So if we look at the long-term slip rate, so the long-term slip rate is the slip rate over 15,000 years, we see that there is a period where there was a faster slip rate, which I'm calling a cluster, and a slower slip rate, which I'm calling an anti-cluster. And there's that change at about 4,000 to 3,500 years ago. So what if I look at another fault in the area? So the Leonessa fault is a cross strike from Monte Vetri. They're about 40 kilometers apart from each other. And this is the slip history from the 36 chlorine. and we see that, again, that there is a change in slip rate at about the same time. And again, we can see that there is a time here where we have slow slip rate and a time here of faster slip rate. So what we see is that the changes in slip rate are actually anti-correlated with each other. One goes fast, the other goes slow. And it's not just these two, we've got other examples all around this area. So I've already shown you that the Monte Vetri fault slows down at about 4,000 years. The Leonessa fault speeds up at 4,000 years. And actually, a lot of other ones also speed up. So this is really puzzling. Why do these slip rates vary? It kind of implies that strain is being shared, but what's the underlying mechanism? So what I do a lot of is looking at Coulomb stress transfer. So Coulomb stress transfer is a static stress change when an earthquake happens. And we know that cumulative Coulomb stress is really useful for looking at the historical sequence in Italy. So is Coulomb stress changes causing these clusters? So these are models of cumulative CS Coulomb stress on faults on the Monte Vetri and the Leonessa fault during the anticluster, so during the time they're not moving. And this is from all the surrounding faults. And what we see is the Monte Vetri fault is positively stressed, but the Leonessa fault is negatively stressed. And negative stress usually says, okay, earthquakes are unlikely. So what we think is that it shows that the Coulomb stress on its own is unlikely to control clustering. However, if we look at the equation for static stress change, what we can spot is that there's shear stress in there. And shear stress is related, it can be given by this equation. And this relates to the shear stress is related to the differential stress and the dip of the fault. So what that means is if we calculate the Coulomb stress, we can calculate the differential stress. Why is this interesting? Well, if we look at the equations for ductile flow in a quartz flow law, which I showed you earlier, we can see that, again, we've got differential stress within there. And because we've got differential stress in both the equations, what we've tried to do is combine these two together. So what would happen if the differential stress change in the shear zone changes? Could that actually explain the change in slip rate that we see from the chlorine? I'm aware I'm slightly running out of time, so I'm going to just talk very broadly. So this is the total differential stress change on the shear zones underneath the Vetri and the Leonessa faults during the time that they're not moving. And what we see is that both of them are negatively stressed. And if you've got a negative differential stress change, because that's proportional to the strain rate, what you would expect to see is a reduction in the strain rate as well. And we can calculate how this would reduce. So essentially, what we see is we take a baseline stress rate, which is based on 10 megapascals differential stress, which is from Baer and Platt, and we calculate the change in strain rate as a result of the change in differential stress. So the important question is, are these magnitudes of strain reduction comparable to the slip rate changes that we see from 36 chlorine? And by looking at the slip rate enhancement, so whether the fault is speeding up or slowing down relative to its long-term slip rate, we see that actually we get really good agreement for the two faults that we studied. So why is this important? Clustering is often really hard to quantify using historical and paleoseismic records because they're so short. So therefore, it's really difficult to incorporate into seismic handling modeling through the coefficient of variation or the aperiodicity. Often the coefficient of variation is constant, but the CV will change whether you're in a cluster or in an anti-cluster, so it depends when you're looking at the fault. So there's a lot of further work to do with this that I won't present because we've not done it. We've got lots of ideas looking at different faults and actually looking at how CV varies. And I will leave my conclusion slide up for you to read. I'm aware I've got a little bit over time, but thank you very much. And yes, please ask any questions, would be great.
Thank you, Zoe. Anybody has a question?
Can I ask a question, Sasha?
Sure.
Hi, Zoe. Thanks for your talk. That was great. So just thinking about the kind of two talks we've had earlier from observational scientists and thinking about your modelling, what kind of information would be most useful from us working in seismic data, looking at the subsurface, or people like Duna looking at the geomorphology? What are the key kind of input parameters you think we now need for seismic hazard models to improve them? Is it going to come from the geometry, or is it actually more the dating and recurrence intervals that are key now?
That's a really great question. That's like the $1 million question. No, it's fine. No, but it's really interesting because I think that, you know, I think it was Pier Francesco Barato brought up in the chat, you know, about how many seismic cycles are in from the work that Bailey looks at, and you know how relevant therefore is the long-term stuff to the, you know, seismic hazard, which is typically concentrating on like what's going to happen in the next 50 years. I would say the answer is that, my opinion would be that what's going to happen in the next 50 years depends where you.
Oh, I think we've just lost you, Zoe.
Well, within a whole cycle, you know, whether you're thinking even when the tip's retreating. Oh no, I've gone, have I?
No, you're back now. You're back.
I'm back. Okay, great. So I think that only by looking at the long-term changes can we actually understand how dependent it's going to be if we only look at a very narrow window from paleoseismology or from historical earthquakes, because that's really what we're very biased against as generally as seismic hazard modelers, is that short window. But how representative is that short window of long-term fault variation?
Great.
So I think, yeah, like I said at the beginning, there's some really nice parallels between all of our talks.
Cool, thanks.
Anybody else has a question? We have a few minutes. Suzanne?
So it's just a very simple question. I was thinking a bit about this, this stress transfer between, I guess I'm sort of stuck in a chicken egg here, but what are some spatial distances over which these stresses can transfer and shear zones can influence each other then?
Again, yeah, that's a really good question. So it's something that we're gonna, so this is one example that I've presented where there are these two faults about 40 kilometers across strike. And it's not just these two faults we looked at, we did look at other ones. And we have got other examples of where there are like pairs or even 3 or 4 faults across strike that are interacting in a similar way. In terms of the distances between faults, it would really depend on how fast the faults are slipping, how big the faults are. I mean, 40 kilometers, and it seems to have a really big, effect. Some of the other examples we've got are over sort of 80 kilometers. So yeah, I guess relatively big distances for Italy, but whether that's big or small for other systems, you know, it depends on the system.
Zoe.
Thank you. Yeah.
Hi, sorry, Chris Jackson here. Just Suzanne's question. I mean, if all of the faults are rooted in the shear zone, then it's more to do with the physical link between the faults and the shear zones than it is the cross-strike distance between the faults themselves, correct? Would that be?
Yeah, no, exactly. So, yeah, I guess I should have said that the Leoness and the Vetri faults are 40 kilometers across strike at the surface, but the Leoness is one of the few faults that dips northeast rather than southwest, so they do actually come like this. So they very, very broadly form a graben structure. But the other examples we've got are faults dipping in the same direction. So yeah, I guess it depends more about what the shear zone geometry is at depth, how close they are at depth, rather than how close they are at the surface.
Because that says something quite fundamentally different to some of Patience Cowie's works about the stress transfer between faults in an array, of course, then, right? So it basically says you could get these kinematic interactions as a function of the shear zone, not necessarily of the stress transfer in the uppermost part of the kind of the upper crust, really, if that makes sense. It's kind of quite interesting, they'd be different.
Yeah, so, I mean, you know, a lot of the work that I've done is also looking at the stress transfer and the brittle part of the crust, but that's looking at it over a different time scale. So whether the difference in timescales of interactions are important, I don't know. But it's a great thing to think, you know, it's a good problem to think about.
Yeah, absolutely. But I could also imagine that that is a quite different mechanism, because if you think about the duct, if it's transfer in the ductile regime, they might even be rooted somewhere in a common.
Yeah. Yeah. So the evidence that we have for Italy makes it seem that they are discrete and localized, and that there isn't some kind of through-going shear zone. That's based on the best data we had. If you had a different fault system with a different geometry of shear zones, yeah, that would definitely make a difference.
Yeah, thanks a lot.
Thank you.
Okay, thank you, Zoe. Thank you all the other speakers. So this will be the end of today's session. In 2 weeks, we have a session on deep crustal imaging with these people on the screen. And so that will be Tim Minchell looking on Galician margin, Kim Welford on Newfoundland, and Emma Chambers on AFAR. And if you don't make it, you can look at the videos, which I just put the links in the chat. And if you are not on the mailing list yet, you can subscribe there to be updated whenever there's something happening. And if you know someone that would be giving a good talk, then please let us know by mail, and then we can invite them for one of the next meetings. And with that, I'd like to thank you all and see you soon. Bye-bye.